Welcome to Data Skeptic and our ongoing series on natural language processing. We've gotten into a good stretch of the season here where I'm talking mostly about translation and the borderline spooky advancements that have taken place recently. I've already hammered home to you that the key to a lot of natural language processing is being able to manage extremely large corpora. And I hope you caught our Elmo episode a little bit ago. We've got a lot more to say on that line of inquiry. Got a couple good shows coming up for you about a lot of the things that were inspired by Elmo, and how we are really at a somewhat interesting and almost unprecedented time, where the availability of these pre-trained models allow a little fish to take the work computed by a big fish and do some really interesting things with it. And we heard some of the challenges to translation in our recent episode, Simultaneous Translation. The main constraint there being, how do you get translation as close to real time as possible to enable good conversations between speakers of two separate languages? Important work for sure, but we don't need real time in every situation. There's other interesting problems of translation as well. And in a world of Twitter and text messages and, well, especially chatbots, I've been thinking a lot about chatbots lately. Why shouldn't that technology be out-of-box multilingual? Well, there are some big challenges around sentence snippets, small phrases. Now, this is not my own unique realization. This was previously recognized by the people managing the Analytic Cup at CIKM 2018 when they launched this Analytic Cup competition. They worked with Alibaba to get a multilingual dataset available and then gave it to participants. And out of that competition emerged a great published paper, Cross-lingual short text matching of question pairs. Link in the show notes. And I brought the author on today to tell you more about the competition, the data set, and the approach to solving the problem.
My name is Asmelash Teka, and I'm from Ethiopia. Currently, I'm doing my PhD at the L3S Research Center in Hanover, Germany.
Can you tell me a little bit about what the LCS Research Center is?
The L3S Research Center is a web science research institute. It has many divisions, but mainly it applies information retrieval, natural language processing, and other techniques to see and understand online data to kind of infer about the offline world.
So I read your recent paper, Cross-lingual short text matching with deep learning. There's a couple of important keywords in there. Maybe to break it down, could we just start with short text matching? What is the essential challenge there?
The problem of short text matching, it can be stated as follows. Given a pair of sentences, a model tries to see if they mean the same thing or not. Here's an example. A pair could be something like how to place an order. This would be one sentence, and another sentence could be how do I place an order. These two sentences mean the same thing. Whereas if we take examples like I do not know the problem and I do not know the website, these two mean different things.
And I think we could even come up with some more challenging cases, maybe like how do I place an order and how do I get the product I want? Are those essentially something we'd want to match in your use case?
Exactly. Those would be considered matches.
I think listeners will appreciate that this is a challenging problem already. Now let's add in the extra layer. What does it mean to have cross-lingual short text matching?
In the context of this competition, what they had was English sentence pairs that were labeled as matches and non-matches. There were 20,000 pairs of them. What they were really interested were in Spanish pairs. They had 1,400 pairs that were labeled. But the question was, how can we leverage the big English corpus that was labeled and to try to kind of work on a less resource language, such as Spanish in this case?
What would the model eventually that comes out of this competition be most useful for? How might someone put it into a production environment?
A model that can automatically tell whether two sentences mean the same could be applied in a variety of applications. One of those use cases is in question answering sites, such as Quora or Stack Overflow, where people might be asking questions in different forms. So if there's a model that can automatically tell two questions meaning the same, then they could redirect and give answers that were given for other similar questions. Another important use case recently is in the development of modern chatbots. People could ask the same question differently. And if the chatbot can understand the intent of different questions that mean the same thing, then it could reformulate and answer appropriately. So they do have really wide range of applications indeed.
You'd mentioned some of the high-level statistics on the data set you had available. From my personal point of view and my experience with some natural language processing tasks, this seems like a rather small corpus of labeled data to work with. Would you agree? Is this kind of on the smaller side of what might be ideal for building a really industrial scale system?
It's true. I would say for current deep learning models, more training data would be better, but it's also very challenging, especially if it is human annotated data. So I would say yes, it's a small scale data, but it's quite decent for what could be done manually.
And can you talk a little bit about the nature of the questions? Were they from any one category or just general, any sort of linguistical question one might come up with?
These were from Alibaba, this giant internet company in China. So they had a chatbot system where they actually had product related questions where people were asking about purchases they made or questions they had about the services. And Alibaba has several services. So these were related to internet uses of different varieties.
Before we get into your specific contributions, can you tell me a little bit about the historical ways people might have approached a problem like this?
So the short text matching would be treated as string matching. Typically, traditional approaches such as TF-IDF or even BM25 would break down a given sentence into the tokens that constitute it and try to look for patterns that occur that might be commonalities or contradictory terms and so on. So these are the traditional approaches. And the problem with these approaches is that someone could express a given intent using different words. These different words that could be synonyms or antonyms and things like that may not be exact matches towards what we're counting in this kind of traditional approaches. That's why we need to kind of go beyond the actual terms that are used and use other representations of the terms.
So, as you'd mentioned, you had these 20,000 English sentences and just 1,400 Spanish questions. Were those already corresponding? Is that sort of the nature of someone hand linked those 1,400 to some 1,400 English sentences, or did you have to start from no links whatsoever?
All the sentence pairs were given with their corresponding translations. So the 20K English pairs were with their corresponding Spanish translations. The same was true for the Spanish pairs. For the 1,400 Spanish pairs, you had also the corresponding English translations. On top of that, they provided around 55K Spanish pairs with their English translations, but these were unlabeled. These were basically the data sets that were provided by the organizers.
So, a major topic in NLP these days is transfer learning. Were you able to bring in anything from, let's just say, the outside, whatever that means, to help in your work?
I would have loved to do that. Unfortunately, there were some restrictions by the challenge. And this is important because, of course, what they wanted was not just the best system that solves the problem, but something that they could deploy in their current system. And so for that, they gave some restrictions, including not to use external data sets, or if you used even other pre-trained word vectors, to stick with only fast text pre-trained word vectors. So for this reason, I didn't experiment with transfer learning, but with the given restrictions, I tried to play and try out different architectures and different setups.
So, going into it, what was your thought on how to approach the problem?
One of the first problems basically was that the 1,400 Spanish pairs was not enough to do any training on its own. In fact, when I started using the given data set as the setup it was, I couldn't do well. So one of the things I tried was, okay, we have around 55K unlabeled Spanish sentences. And if we can somehow tap into those unlabeled sentences and augment our given Spanish labeled pairs, maybe we could do better. So this was one of the first insights that I had to kind of find out somehow from the unlabeled Spanish sentences, mine or mint some labeled data from there and increase the number of training set.
That's very interesting. Can you talk more about that process? How did you end up minting yourself some new examples?
So I tried a couple of approaches. One was, of course, to cast this as a classification task. Since we have 20K labeled English sentences, one idea was to use these English pairs as training. And since we have the corresponding translations in Spanish, and then try to apply that on the unlabeled set. This turned out to be okay, but not quite good for the training set. Remember that if we're going to use whatever we are minting from this unlabeled set into a training set, it better be very high quality. We have a stringent requirement that it has to have a very good accuracy. Unfortunately, this classification didn't give me good results. So I had to resort for a very simplistic yet realistic approach, which is basically to try to see, okay, if we can find matches from the English pairs that we already have that really match the same English sentences in our unlabeled Spanish pairs, then we can consider them. So it was basically an exact match, but destroying the order and the casing and stripping of punctuation and subwords.
Normally that you could say that that's sort of like there's an information loss in that process, but in this case, it seems like you might be able to get some pretty good matches. Can you talk a little bit about, I don't know if you have an accuracy score on that or just a general sense of how successful this kind of crude technique was in getting you what you needed?
Right. It is, in fact, not a bad approach. Of course, I would have loved to do more. It's not easy to do like absolute precision and recall measures on this, but you can actually evaluate the relative precision and recall in the sense that, let's say, out of these 1,400 Spanish pairs, how many of them would I have generated if I used this crude technique, let's say? And it turned out the relative precision was good. It was 97.82%. When I inspected some of these mislabeled instances, it was errors in the training set. They were, in fact, good matches. But the recall suffered a lot because, as you said, we're looking for exact matches, and this doesn't bring the more novel and interesting kind of matches. And it was 8.3%. So this was how I measured how well this unsupervised way of generating pairs worked.
Thanks to this week's sponsor, the Great Courses Plus. Have you been to thegreatcoursesplus.com/data? Let's do it now. Now you got 12 categories, but if you ask me, you got 3. Science, economics, mathematics. If your statistics are not on point, you go to mathematics first and start with probability made clear. I can't emphasize enough how good you need to be with your stats. When you get that on point, take a saunter through economics. Try the economics of uncertainty. And in science, honestly, you can't go wrong. We all have our preferences. I was more of a space guy than a biology guy, but they got you covered no matter what. You can access these courses anywhere, anytime with the Great Courses Plus app. Learn at your pace when it's convenient for you. Data Skeptic listeners, special offer, of course, but the deal is really sweet. Not only do you get 1 month free, but you get a second month for 99 cents. Have you done this yet? Have you lost your mind? 2 months? 99 cents? You can't check it out? Everybody, you owe it to your brain to head over to thegreatcoursesplus.com/data. So the ultimate machine you want to create here, I guess, takes in one English question and one Spanish question and is sort of a binary classifier that says yes or no, are these the same question? Yet there's a lot going on under the hood. Can you get into the novel contributions you made and how you built the system to work?
Unfortunately, I didn't actually take the English and the Spanish in the same model. I actually tried that and it didn't work out well. So instead, I had to stick with a monolingual architecture. It either takes English pairs or Spanish pairs. And since the English pairs were not given on the test set, there was no way to use that for the actual testing set because in the test set, they only provided Spanish pairs. Ultimately, the final model, it actually took a pair of Spanish sentences to determine whether they meant the same thing or not. The overall architecture has 3 components. So we have the representation component, that is how should we represent our input? And then the sentence representation learning, how can we learn what the actual sentence means? And finally, a matching function that takes these 2 sentence representations and says, yes, they do match or no, they do not match. So in the literature, there are already a couple of ways of encoding the input at character level or word level. For the sentence representation, we have different kinds of architectures, such as feed-forward neural networks, or DNNs for short. We have convolutional neural networks, CNNs, and recurrent neural networks, or RNNs, and there are different varieties. Also, in the literature, there are different ways of computing the matching function. Some heuristics, such as cosine or dot product on the 2 representations, or a more elaborate machine learning approach, such as applying multi-level perceptron or neural tensor networks.
Let's delve into each independently, the representation learning and the matching function. Perhaps starting with the representation learning, you seem to have like an ensembling technique in play. Can you tell me a little bit about the choices that led you to that architecture?
To start with, I say the inputs were passed through a word embedding. I used the fast text embedding, which was the one that was required by the organizers. And then I tried to see how CNNs and recurrent neural networks worked on this separately. And my intuition is that CNNs and LSTMs or BiLSTMs do capture different aspects of the sentence representations. My intuition was for the CNNs, they were looking for n-grams, this term n-grams. If we took, for instance, a CNN of size 2, it would be looking at bigrams, or 3 for trigrams, and so on. Whereas the LSTM was looking for small and longer range patterns in the sequence. And for the bidirectional, I assume before inferring what a given term means, it would look both the terms that came before it and the terms that went after it. So it occurred to me that they all capture different aspects of the sentence. So why not bring them all together? In this architecture, after we encode these pairs of sentences independently, we pass them through CNNs, LSTMs, and BiLSTMs. And of course, there's also one more architectural choice here. Do we encode each of these sentences separately, or do we make them pass through the same architecture called the Siamese network? Since both of these sentences actually refer to the same thing in the sense that they are from the same domain, as opposed to, say, if you're working on a Q&A system where the question could be a very short sentence, but the answer might be a longer one, and so on, my choice was to stick with the Siamese network. That is, to use the same network for both the input sentences. After letting them pass through this same network that contains CNNs, LSTMs, and BiLSTMs, the next step was to concatenate these output vectors and perform an element-wise difference and dot product for the representation. This would be the output of the representation learning layer.
You gave some very intuitively understandable explanations of what you imagine those three different architectures might provide or might see in the sentences, if that's a fair anthropomorphization of what they're doing. There's a lot of discussion around deep learning and its interpretability and that sort of thing. So it's neat that at a high level, you do have some expectation of what's coming out. Were you able to capture anything, I don't know, a bit more empirical that gives you a sense that indeed you're getting, this n-gram kind of qualities out of CNNs and the qualities you're expecting from the other architectures as well?
I didn't do any experimental evaluation on what they do represent, and I believe that would be an interesting task to do actually. But that was my intuition of what might be happening. Regarding the interpretability, I completely agree. So at this level, I was more interested if they could capture all these nuances than really how they were actually doing it. But following up that work of like what's really happening inside is an interesting pursuit.
The result of the representation learning layer, I guess, is that concatenated feature vector of all of the features you've generated from the different neural architectures. Can we talk a little bit now about the matching layer? You'd started to mention the differencing in the product. What's the motivation to difference and take a product? What do we expect to get out of that step?
Theoretically, we could just take the raw vectors and perform any nonlinear function, such as multilinear perceptron, and get the result. But there was a paper that showed that by doing element-wise difference and element-wise product, you kind of converge quickly and get better results. This is something I took from the literature that showed that this is indeed better when you want to compare two vectors. By doing this element-wise difference and product, you converge quicker and get better results.
Can you talk a bit about the motivation to use the multi-layer perceptron instead of something more rudimentary like the cosine similarity you'd mentioned?
I thought, yes, once we have these representations, I thought it wasn't enough to just do a dot product or a cosine similarity for the simple reason that they could be more complex than I really thought that they couldn't be captured. In fact, it's not only I thought, I actually tried, and the results showed that it was worse. So experimentally, I could obtain that by doing a more complex nonlinear function and using a multilinear perceptron, you could achieve better results than if you just do a dot product.
So after completing the architecture and getting everything fine-tuned, how did your system end up performing in the contest?
So it wasn't bad. This competition had two phases. In phase 1, we had 5K Spanish pairs, and in phase 2, there were 10K Spanish pairs. In phase 1, the evaluation metric was the log loss. In phase 1, the result was 0.35, and it ranked 15th. In the second phase, the log loss was 0.39, and the ranking was the 13th out of 1,027 submissions. But of course, not all methods that performed well in phase 1 may perform well on phase 2 as well. And so the overall ranking was 7th out of the submissions.
Gotcha. And that, I presume, is on the holdout data that you didn't see, not the training data they provided. Is that correct?
That's correct. These were holdout set. One interesting difference for why, for instance, the method, my method performed worse on the second phase was because of these out of vocabulary terms. It turned out that in the training data they gave, most of the vocabulary you can actually find in the fast text list of vocabulary. Whereas in general, their holdout dataset had more out of vocabulary terms. That is terms that you cannot find in the fast text word embeddings. What that means is you don't have word embeddings for them. So they would be represented as a random or average kind of vector. This was one of the main difficulties in the challenge.
I'm curious how you feel more data might have impacted the problem. As we talked about earlier, there's sufficient data here to do an interesting project, but certainly not at the web scale corpora that some projects are built on. How do you think your methods would scale up?
They would do really well because they're really hungry for data. These models, they learn better when you give them more data because the capacity of these models, it can accommodate more varieties, and the more varieties you give them, the better. And in this competition specifically, the way I generated the training set is actually based on the simplistic approach I told you of leveraging this unlabeled data. If we had natural Spanish sentences, even at the scale of the English they provided, then the results would have been dramatically better because the same model, when you try it on English, was performing better than on the synthetic Spanish data that was generated.
So where does this work fit into your overall kind of research and things you're doing? Is this just a side project, or was it core and central to a lot of your activities?
The project started as an interesting side project, but in fact, it's core to my research because basically what I do is applied machine learning for data from social media. And social media, such as Twitter, as you know, is full of short text. And the task of short text matching is at the heart of many of the tasks you do with social media analytics. So it turned out to be a very interesting and core part of my thesis.
Gotcha. And tell me a little bit more about yourself. Where are you at in that PhD process?
So I'm finishing up my PhD very soon, and I'm looking for opportunities where I could apply the skills I have. And so if there's anyone listening and interested to work, please get in touch, and I would be very happy to talk to you.
And where can people follow you online, or just get in touch in general?
I am on Twitter, Asmelash keep in touch.
Cool. I'll have that in the show notes as well for people who want to find it that way. Oh, and one last thing, just curious. Are you a Spanish speaker?
Not at all. I don't speak any Spanish, but as you see, deep learning helps you speak different languages that you have no idea about.
Yeah, this is a funny trend I'm seeing as I talk to more and more NLP researchers, that you're doing research on languages you don't speak or even read, which is fascinating.
One of the things that I'm actually quite excited about is the applications of deep learning and machine learning in general for under-resourced languages. Take, for example, languages such as Tigrinya or Amharic that are based in Ge'ez, that are spoken in Ethiopia, where I come from. There's little work to nothing from the big corporations because they don't see the money in it. And one of the things I'm quite passionate about is to follow up this on these kind of languages.
Oh, that's very exciting and inspiring. Well, Ovilus, thank you so much for taking the time to come on the show. Really interesting work. I'm glad to hear that this competition existed and that you were a participant and shared your approach to it.
Thank you so much for having me, Kyle.